Well, I'm really excited to welcome John here. John is a colleague, a friend, co-founder at Zyverge. So I'm really excited to have him here. And today we're going to be talking about ZIO HTTP. I think that's probably a library that a lot of you are using and have been using for a long time, even when it was in various release candidates. And I think a lot of people have been rightly asking, when is a final stable version going to be out? And I think we kind of like ZIO, we've been close to it a bunch of times, but each time we find more things we want to make better and we kind of push it out. But I think we are just about at the end of the road there. So I thought this would be a fun time to have John on to talk about kind of the final steps of the road there. And then next week, we're going to have a really exciting special edition of Zymposium where we're going to be talking about the other thing that a lot of the folks you've heard from have been working on. So John and Daniel and I and some of our colleagues at Zyverge have been working on something new called Golem. And we're going to be announcing that publicly and letting people start playing with that next week. And on Friday, we're going to have a symposium where we get the whole development team from Golem together on here, and we live code an application together on it. So I think it's going to be really exciting. And if you downloaded it at the beginning of the week, but you got busy with work and you get a chance to actually do something with it, I think it'll be a really cool opportunity to dive in together. So lots of exciting stuff coming. But today it's all about ZIO HTTP. So with that, maybe, John, let me hand it over to you a little bit and tell us what you've been doing.
Yes. So I have been up to a lot of things. I've been sort of obsessively, I think, going over the last mile of ZIO HTTP. Previously, I had gone through things like request and path and just data type after data type, trying to bring this sort of very high attention to detail that you see in the ZIO core library itself. Like our names are consistent. Our methods try to be logical. We try to make sure everything is as orthogonal as possible, compositional, type safe, just checklist after checklist after checklist. And I've done that over the past, I think, 3 months roughly. I've spent a lot of time on ZIO HTTP, just trying to polish and get things in place. And there was this one part that I had been avoiding intentionally, and I kept on pushing it off. Just down the road, and I'll get to that later, almost done with ZIO HTTP, except for this one area. And that one area was actually the heart and soul of ZIO HTTP. It's the heart and soul of any HTTP library. And it's the part that allows you to define routes and handlers in middleware. And there's actually not a lot of data types involved in that. I mean, there were a lot prior to the refactoring, maybe 10 or so, but it's been simplified. And the reason why that has taken, I think, so long to get right is because there's not one answer to the problem of how do we define routes, how do we define request handlers, how do we define middleware. There's lots of different answers to that question. And I think that the design of the Scala libraries has been largely consistent on using a model of a request handler that is a partial function of request to response. And I think, Adam, you covered this in last week's session or the week before, not too long ago.
A couple of weeks ago, yeah, we did a session talking about partial functions in general and the limitations of partial functions and doing a toy version of kind of what a router would be and why that might be pathological to compose 100 different partial functions together.
That's right. So Adam has prepped you well for some of the changes that you're about to see today. Basically, it's a beautiful idea. A request handler as a partial function doesn't work out all that well in practice. And when you go away from that, you're exploring uncharted territory, at least in Scala. Obviously, every programming language, every ecosystem has its own answers to these questions. But the question is, what should ZIO do? What's right for the ZIO community? What makes sense and fits into everything that's out there? And we've had several answers, I think, over the past 4 months. And we've been exploring, we've been learning, ultimately, in order to correct a lot of problems with middleware. we had to refactor the design. We extracted two things that were previously one concept. So there's one concept, ZIO HTTP, like many libraries out there, have started with this one concept. And ZIO HTTP called it an HTTP. And an HTTP was basically a glorified handler that also embeds this notion of partiality into it. And it became clear when we were working on middleware for ZIO HTTP that entity was too powerful. It was way too powerful. And in order to have well-defined semantics for middleware, and an example of well-defined semantics for middleware is the ability to say that these middleware should apply to this route, and these other middleware should apply to this route. And we don't want those middlewares running for the wrong routes. And actually, that's very, very hard to achieve. But to solve that problem and some other related problems, what we had to do was take this hugely powerful construct, the HTTP, and we had to tear it apart into two different pieces. And in the most recent refactoring, prior to the most recent refactoring that I've done, these two parts were called HTTP and handling. Okay, and a new design. At that point, it became clear to many of us that a new design was emerging. So a new type of HTTP library was emerging there because we were separating things that had previously been merged together under a single entity. And we were doing that to make them less powerful. And to make them less powerful, we're constraining them in ways that give us more flexibility in the implementation. And that's really what having well-defined middleware is all about, as well as performant route handling and all that stuff. It's constraining these data types enough that we can have very efficient, powerful ways of composing them and then executing them and dispatching them. And so we pulled them apart into the handler and the HTTP. And then there was still too much overlap. I received comments from many of you actually, like saying the pieces aren't fitting together quite correctly. And that's because we went part of the way there, but we didn't go all the way there. And what's all of the way there? Well, that's what I'm going to show you today, is the design that I ended up settling on that feels really, really good. It feels solid. There still might be a few edge cases that I hope you'll help us discover as we push out this last planned release candidate for ZIO HTTP, but it feels really solid. For the first time, I can say why there are these different data types, why they have these names, what their function is, and I can show you how they relate to one another. And it's all fitting together as well as I have ever seen it before. So let me go ahead and share my screen. And I'm going to show you basically the changes. So that tiny little bit of ZIO HTTP that I put off for weeks and weeks and weeks and finally got to, and I put it off for a good reason, by the way. My pull request was almost 8,000 lines of code. So it is a major, major change to the library. And it's just something that had to happen before we push this out for a long-term stable release, which is what we intend on doing after these changes. Let's go ahead and share things, and I will give you a sneak peek at how things look. Okay, so first off, all of the pattern matching in ZIO HTTP is gone. It's all been ripped out. It does not exist in any form. There's no more pattern matching. In its place, a DSL has been introduced that is somewhat similar to pattern matching. You may like it, you may not. You don't have to use it, however. With the old pattern matching DSL for routes, you pretty much had to use it because there wasn't another effective way to do the same thing. But with this new DSL, you can sort of take it or leave it. The core thing, the core entity in this DSL is something called a route pattern. Adam, did you talk about route patterns at all?
We did a very simple version of it.
Okay.
So
All
not nearly as much powerful to kind of extract variables as this, but very, very simple.
All right. So let me just show you this entity here, a route pattern. A route pattern is a very, very important concept in the new ZIO HTTP because it defines what your routes look like in a way that's a pure value. And this has a ton of benefits. Obviously, it has benefits for performance because we're able to do very efficient dispatch, but it also has benefits for things like request logging and metrics and whatnot, because now for the first time, we have a concept of this handler will handle routes that look like this. Now, route pattern is basically a combination of a specific HTTP method, and method has been generalized here so that if you don't care about which method you're dealing with, if you want to sort of match all methods, then you could use method any. Method.any would be the sort of pattern that allows you to match any method. And then we have this new thing called a path codec, which allows you to basically extract out a path into a value of type A and turn a value of type A back into a path. So it's a codec in the sense that it allows you to take this path and go to a value as well as to go back. You can sort of deserialize or decode, if you will, and encode it. And this defines actually the pattern. Well, actually, this defines the method pattern, and this defines the path pattern. And how you build these things, well, you could build them actually directly in here using the constructors. So you could say route pattern get, for example, would be a pattern that matches the get HTTP method. And then if you did not extend that pattern with any path codec, then it would only match the root path. However, you can extend these route patterns by using the slash operators. So the slash operators here, actually, there's just one of them that takes a path codec. And what it does is it takes a new path codec and it appends it to the previous path codec. So once you start out with the base pattern, you're matching the root. And every time you append a new path codec, you're matching some child of what you had before. So you use slash, and then you can specify any path codec here, and there's a variety of different path codecs inside the companion object of path codec. For example, there's one that will match an int segment inside a path codec. There's another one that will match a literal inside a path codec. There's another one that matches a long, another one that matches a certain any string at all, and another one that will match many segments of path. So basically, this is your remainder. It's the path remainder. I want to eat up all parts of the path segment. And then there's one for matching a UUID. Path codec has a very, very low level, very efficient means of, actually, you can see the code here. Here's the code for decoding a path into a value of type A. And this is extremely low level code here that has been heavily optimized. And it's designed to minimize allocations. It brings it to its theoretical minimum. And how it does that is it actually, beforehand, it optimizes the path codec into this intermediate representation that is called an op. It actually produces an array here of this opt data type. And this opt data type is a virtual machine, if you will, for performing decoding on a path. And it consists of a number of different instructions. It's a stack-based virtual machine. And it consists of a number of different instructions here that operate on the stack, as well as the next input segment from the path. And you can see here, it's very, very simple, very, 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 very tight. And it's used heavily in decode in order to do almost zero allocation decoding from the path. It's not quite zero allocation because we need a stack. So we're using an array stack here. So hopefully in the best case, we just allocate an array stack of size 2, and then we use that, and hopefully we don't have to change that. And I think for the common case, that's true. We're allocating an either there, but then as you can see inside this loop here, it's just super tight iterating on an array. So it's able to benefit from cache locality here in the CPU. And none of this code here does allocations. It's all of these things here are array accesses. So we're accessing by index in an array, which is a very efficient operation. And just everything is super low level. These strings are formed and only in the event that there actually is a failure. So that these allocations only occur in the unhappy path, not the happy path. And all of this is just sort of special case. So what this gives us the ability to do is to very, very quickly decode a path into an A and hence match one of these path patterns. And then let's see, let's go back to route patterns. So these route patterns can be formed. And when you form them, then you are able to apply them to a combination of a method and a path to see if they match. And if they do match, you can produce a value of type A. Okay, so that's actually here in decode. When you decode on a concrete method and concrete path, either it's going to fail with a descriptive error message, or it's going to succeed with a value of type A. These have rich renderings. So the toString here, actually the render method uses the HTTP method, followed by a very high level and very nice, exactly what you would get from OpenAPI, really, rendering of that path, including variables for any placeholders in that path pattern. And then this can be converted to an HTTP codec, which is used by the endpoint API. So this new route pattern, you can actually build one, like I said before, by starting out here and then using that slash operator on path codecs. But you don't have to. What I did is I introduced basically a very small DSL that is designed to start at the same place the previous pattern matching DSL started, which is this HTTP method. So you can start here with any HTTP method. And then when you call slash on that, this is a method on this data type that is going to expect one of these path codecs. And what this will automatically do is it will build a route pattern for you. Okay, so this actually gives you a route pattern. And every time you call slash on that, that is actually the slash operator on the existing route pattern. So you're building deeper and deeper route patterns. So you end up out of this with a route pattern. And that is 1/2 of a route. So a route is a new thing. As part of this refactoring, it is a new thing. And a route is basically a combination of a route pattern and a handler that is designed to handle the requests that match that route pattern. Okay, you can think of it as a tuple. And in fact, this operator here is designed to suggest the tupling, because a route really is a tuple. It's not the tuple operator. This is actually an operator on this route pattern, which given a handler will build you a route. If you hover over this type here, you can see we have a route. Route has two types. Let's take a look at that. That's the next step in this exploration. What is a route? Route has two type parameters. Oops, that's not. Route can be thought of as a tuple of your route pattern and your handler. Okay, so it's just a tuple and it has the pattern and it has the handle for requests matching that pattern. It has two type parameters, and one of those type parameters is the environment that is used by the handler. And then the other type parameter is the type of errors produced by the route. Another big change in this refactoring, this final refactoring in ZIO HTTP, is that I think we have a very good grip on the error story, and we're always going to force you to handle, actually absolutely force you to handle every possible class of error, including defects. Now, there are convenience methods that you can use that let you tell the library, just do whatever you think is best. But at the end of the day, you will be forced to handle basically every cause of failure that could possibly occur in the handler and translate that into a well-defined response. And this is great because you never want to call into REST API and have undefined behavior in the event of an error. That behavior should be well-defined, and the client should get back a suitable and appropriate response, which helps them diagnose the issue. And here we are using the static type system of Scala, as well as techniques in functional programming to basically guarantee that that happens. So a route, you can only do a few things with a route. One of the things that you can do is you can transform the handler. But you can also see the location at which this route was defined. So for diagnostic purposes, every time you make a route, we're capturing the location where that route is defined. And that can be used in metrics, in request logging, and all sorts of things. All this new functionality being powered that was not possible previously, which is possible now. You can convert a route to a handler, but you can only do so if you have properly translated all errors into responses. And you do that with the handle error method. Handle error is a bit like a map error, and handle error cause is a bit like map error cause. However, what these operations do is they fundamentally change the type of route. There are basically two fundamental types of routes. One is the type of route that has not worried about its errors yet. Okay, so it might have defects, it might have all sorts of problems that have not been dealt with yet. It might have typed errors, and you just want to defer that until later, because in many cases it's convenient to stitch all your individual routes together into a bigger structure and handle all your errors at the same time. So we allow you to do that, to defer the errors until the sort of last possible moment. And ultimately, at the end of the day, though, you're still going to have to handle them. When you do handle them, what happens is every individual route is transformed from this type that is not guaranteed to handle its errors into another type that is guaranteed to handle every class of error. And that's when you're sort of golden. When you've done that transformation, when you've baked your routes fully, so to speak, and it's ready to come out of the oven, then that's where you can move over into the world of HTTP apps, which is something that I'll show you in a bit. So you can get out the handler from a route by calling toHandler. This is like it's actually the final handler. So the handler you get out of here, it will fail with a response or it will succeed with a response. You feed it a request, and no matter what, in all cases, you're going to get back a response. And then you can also get out the route pattern associated with this, which can be used for diagnostic purposes. All right, so back to our little hello world example. This is the route pattern. This is a method on the route pattern that takes a handler, and the formation of these two things gives you back a route. Well, what do you do when you have a route and you want to go to the next step? The next step is to take your individual routes and to combine them into this data structure called a routes. And routes, you can see it here, it's like a collection, it's like a list. And in fact, if you look at its definition, it's just a very simple data type that is literally a chunk of individual routes. So very, very simple. This is the replacement for HTTP. So in the old world, we had HTTP. In the new world, we have routes. And HTTP was a very complicated structure that overlapped a lot with handling. And it was not clear where to put things. And in fact, in some cases, you might want to put things in both places. In this new world, we have the handlers, the request handlers. We have the routes, which add to a request handler. They add a route pattern. And then we have routes, which is a collection of individual routes. And this is just an ordinary chunk of route. There's no magic going on here. There's no complexity. This is just a new type, if you will, that allows us to add specialized operations onto this data type that makes sense for a collection of routes and that you will commonly want to use. There's no reason you couldn't use a list here. So there's no magic. This is the direct analog of the old HTTP. And it's very well structured. Like you couldn't, in the old days, you couldn't enumerate over routes because all you had was this partial function. You couldn't enumerate over and generate anything, documentation or efficient dispatch trees. You couldn't do anything with that. But in the new world, all you have is this individual chunk of routes. You can see how long it is. You can see how many there are. You can see all the different patterns. You can see if there's any overlaps. You can really do a lot with this structure. And it's the unification in ZIO HTTP of this lower level means of defining individual routes by specifying the patterns and the handlers. And then the higher level means, which is located in the ZIO HTTP endpoint package, which allows you to define individual endpoints and implement them. When you implement an endpoint, guess what you get out? A route. So they've been unified. These totally separate worlds that spoke different languages in this PR that is already merged in, by the way, it was merged in yesterday into ZIO HTTP, they have now come together. And no matter how you choose to create your individual routes, you end up with a route data type, and these compose together. And then when you convert that into your app, they're optimized together. So dispatch happens on the entirety of all your routes, whether they were defined with the high-level endpoint API or the lower-level route API. This has standard collection-like operators, but it also has this interesting operator that you're going to use a lot that is reminiscent of the at operator on the old HTTP that takes something called middleware. So I'll talk about middleware in a second, but for now, we're just going to skim over this. You can handle every errors. And a lot of these methods are just sort of mapping over the chunk and applying everything to all. So they're very, very straightforward, very logical. There's no complexity here. It really is a simple idea. And then there's this new operation. Go ahead. Question?
Can we hit on a couple questions here just
Yes.
before we go past the routes?
Sure.
So one question was, how do you deal with duplicate routes? And I think basically the semantics is first match wins, just like the partial function, but check me there.
Yes. Yeah, that's right. So duplicate routes, basically the order of things is it's left biased. So if there are duplicate routes, then the left one will handle it. And there could be overlapping as well. However, if the left-hand side returns a not found, then we're going to pivot over to the right-hand side. That allows you to have some sort of degree of dynamism. That's sort of the old notion. You can have selective dynamism here in your new. So if you say you handle everything, but really you can only handle a few things and you can only know that dynamically, you can still do that using this routing machinery. Of course, you're going to pay a performance tax for that because the old means of combining using or else, which has been sort of replicated here as a fallback, is not that efficient. So I don't recommend having overlapping routes. And actually, in the future, we can have an operator here that looks for overlapping.
I was about to say that, yeah.
Warns, and says, "Hey, you got a problem here." Also, another wonderful thing we can do. I'm going to make a ticket if there's any interest in anyone doing this. But basically, is have an amazing not found handler. So when you go in and you get a not found, you should get back this beautiful HTML page that says, "Hey, this route wasn't found, but there's these other 4 routes that are somewhat similar. Maybe you met one of those," and that's going to be great developer experience to have that. And it's not something you could do with a partial function. But here we know exactly sort of how close you are to all the routes in the system, and we can say, "Oh, it looks like you're trying to get one of these. Maybe you need to add this," and so forth. That's going to lead to a really wonderful developer experience.
Yep. And then the other question we had was, can you still implement custom HTTP methods? So like someone had an example where they had a method and it was just called join. And how can we express that in this?
It does not change. It does not change. So you would just do method.custom join. So, and then that would match against that specifically. So you've not really lost, I don't think you've lost any expressive power. There's a few differences, but you can still do custom HTTP methods.
Got it. And then I think you have a plant in the audience because there's someone who asked, could the routes be combined into a tree? This should be more performant.
Yes. Yes. So let's talk about that.
They already are.
Yes, they already are. They already are. So let me just mention a couple more things here, and then I'll move on to talking about trees because that's important. So this sandbox operation is new and useful, and what it does is it gets rid of your E. So you call sandbox, and you're going to delete your error, and you're going to move into a world in which everything is totally sandboxed. Every error has been handled in some fashion or another. So you could call this if you just want to sort of cheat and say I don't want to worry about my errors, or you could call handle error cause and sort of provide your own custom mapping from every one of your error types into something else. Over time, we'll probably improve the way this works. I'm probably going to make a ticket about that as well, but it's here now, and it does a reasonably good job of sort of converting error types into HTTP response codes in as best a fashion as possible. And obviously, a lot of things go to internal server error. And then there's a timeout ability. Okay, so once you assemble your routes and you maybe apply some middleware and maybe you do some timeouts and sandbox it, there comes a point where you need to actually build the HTTP app that you're going to deploy on the server. And you do that using 2 HTTP app. And you can only do that after you've handled all your errors. So once you've handled all your errors, you are now able to build an HTTP app. And an HTTP app is nothing more than a simple wrapper around routes whose errors have been handled. So again, complexity is sort of going away, just very simple data types, minimally polymorphic, very simple data types. And this HTTP app represents something that can actually be served. The other ones cannot be served. because maybe the errors haven't been handled, or maybe they have not been converted into this app. HTTP app used to be a type alias for an HTTP, but that's not true anymore. But you can see it's sort of, almost equivalent, right? But because if routes is the new HTTP, then it's kind of like we have a type alias here. But I'm not a big fan of type aliases because they don't give us a place to put domain specific methods and constructors. And that's what we have here is, this is an app. It's ready to run. So we have methods and constructors that make sense for apps, but don't necessarily make sense for other things. And one of the things that you're going to see if you examine the body of it, first off, some methods have been replicated just for convenience. Basically, because HTTP app is a route, it's a route where all the errors have been handled. There are some replication of methods to allow you to do something either at the routing layer, or if you built multiple apps and you want to compose them together, you can do that as well. But one of the most important things, you also have run methods. Okay, so you have run methods, and you can convert a app into a handler that fully handles all of its requests and returns well-defined responses, and that's guaranteed by the process. It's not possible to construct an HTTP app handler that does not handle all requests and return well-defined responses. You can time out things at the app level, which is just a delegation to the route stuff. And this is where the magic happens, conversion to a handler. So in the old ZIO HTTP, there is a ridiculously inefficient process that unfortunately is inherited sort of from all the way back to Blue Eyes, the first web framework that I made, which defined a request handler as a partial function. And composition of routes in that world occurs using or else. And so what that means is all these combinators that allow you to sort of pattern match on the path, they have to pick apart the path component of a URL. And that involves lots of parsing. So every single time you do or else, you are picking apart the path, parsing it. And in many cases, you're parsing it to very similar structures because all of these routes start with users and whatnot. And so a ridiculous amount of inefficiency is caused by that in the old design of ZIO HTTP. And in the new design, we don't need that because we have this new thing called the route pattern. So rather than sort of trying everyone one at a time and saying, does this match, or does this match, or does this match, and so on, and picking it apart a billion different times, what we do is we actually build an efficient prefix tree. So that's this tree here. This tree is built on demand. So as you dynamically compose your HTTP apps, you're free to compose them as often as you want. This tree is built dynamically on demand, and there's a cost associated with building this tree because it's basically an index on all of these routes and whatnot. But that happens on demand, only happens one time. So once you've assembled your final HTTP app and you've gone to serve it, and then the server calls to handler that first time, then that's where the tree is materialized. And this tree is, let me just show you what it looks like. It's kind of hard to see because this tree is built on another tree, which is the route pattern tree. And the route pattern tree is built on another tree, which is segment subtree. Yeah, it's built on segment subtree, which occurs in a path codec. This is the underlying thing here. And what this tree is basically it's a mapping from its fast path case is where it's picked apart a path and it has a path segment, for example, users or orders or something like that, and it feeds that into this map structure and it gets out all the trees associated with that. But there are also cases where it might be an integer or it might be a Boolean or something like that. You've got a variable, and so that's handled by these other cases. And the segment subtree is basically these trees of similar things that has very efficient lookup method. Here's the lookup method here, and you can see some very low level code here. It's very low level, zero allocation code. Everything that can be done in advance is done in advance. We're using chunks here whenever we can for efficiency. We use list maps to preserve order, but also to allow us to have log and lookup. So very, very fast lookup from these essentially hash maps that we're getting out of here. And this lookup process here has almost zero allocations. There's one allocation here in the tuple that we have to return from here, but I think that's the only allocation that occurs in the lookup process. So very fast ability to sort of zoom into this big tree, prefix tree, and find the route or route handlers that match that given pattern. And it does not affect the semantics or the usability of this data type in any way. There's no formal step of building that tree. It's just automatically built on demand and memoized as part of this HTTP app. All right, so let's move on to, you've seen now a route pattern, which is a pattern of a method pattern and a sort of path pattern. And you've seen how if you combine a route pattern with a handler, you get back a route. So a route is basically a tuple of the pattern and the handler. And then you've seen if you combine multiple routes, you get back this route structure, which is just a chunk of routes. And then once you handle all your errors, you convert that to an HTTP app by calling it to HTTP app, and then you can literally hand that off to the server and they can serve it. What you've not seen is the redesign of middleware. Middleware is extraordinarily tricky. It's just very, very complicated because there's all these different trade-offs between how fast you make it and how powerful you make it and what sort of guarantees you can provide and whatnot. And where I ended up is I ended up on essentially two classes of middlewares. They're not called middlewares. Only one of them is called a middleware, but basically two classes of middleware-like things. And the more powerful one is this thing called middleware. In theory, by the way, it's possible to have more classes of middlewares, but I don't think that that matters to a user. And when you're thinking about middleware, you just want to like grab one and apply it to something. Right? And so that's what this library has now been designed to do, is eliminate all that complexity and also embrace familiar terminology. So if you need middleware, you can probably get it by going to the middleware companion object and just applying it to whatever you're trying to apply it to right there. So this is the important one. This is the one you need to know about. And middleware could be viewed as a function that takes routes and returns routes. Okay, this is a very powerful definition of middleware. Why? This definition of middleware can remove routes. It can add routes and it can modify routes. And in modifying routes, remember what a route is. A route is a tuple of a pattern and a handler. So middleware can also modify a pattern and it can also modify a handler. So this definition of middleware, it can do everything. However, as a consequence, it's not necessarily going to be extremely efficient. These definitions, this is an executable encoding of a middleware, and you're going to end up if you did everything through this definition of middleware, you would end up adding a lot of overhead, and that overhead would be impossible to optimize. So I'm going to say this is the middleware definition you should probably use when you can, and you think about middleware in these terms. It's a transformation of this collection of routes into this other collection of routes, where maybe the route patterns and the handlers have been modified, or maybe new routes have been added. Maybe some routes have been subtracted. Middleware has full access to the routing table, full access to the handlers, full access to the patterns, can do whatever it wants. And examples of things that can only be done with middleware that this powerful is cores. Why cores? Because cores, you have to both modify request and response, but also add new routes. You actually add a new route as part of cores that's able to handle options for any path. So you have to do both of those things as part of the cores middleware, which is why it's here. In addition, request handling is about to land here, and that's because request handling really wants access to the route pattern. It doesn't really, we had this weird thing called a path label mapper, which would map a path into a label to be attached to the logging, and now that's gone. Basically, it's gone because we don't need it anymore, because we can use the route pattern. And timeout here is an example of another one, which, well, you don't have to do this here, but it can make sense to do that. All right, so this is middleware. It's just basically a transformation of routes to routes, and it's very powerful. There's one more thing I want to show you, though, connected with middleware, and that is something less powerful, but also way more precise, with an ability to do some very impressive optimizations that you can expect coming down the road. They're not done yet, but they're really quite impressive. So let me show you this thing called handler aspect. So handler aspect is called handler aspect because it's a bit like a ZIO test aspect. Test aspect has the ability to modify a ZIO test, and a handler aspect has the ability to modify a handler, actually a specific type of handler, a request handler. So these handler aspects are defined with respect to handlers that handle requests and responses, basically. So not just any sort of handler, but a handler that's specialized to the domain of HTTP, so request handling. And you can see that inside, there's apply handler context and basically apply handler. These allow you to transform handlers. So these handler aspects are transformers of handlers. However, they can only transform handlers in very specific ways. They are heavily constrained. And that's because they are defined entirely by this new structure called a protocol stack. A protocol stack, something like a protocol stack, sits at the heart of many network-oriented libraries, including, for example, a Netty. Netty has this notion of handlers, sort of inbound and outbound handlers. And JGroups was one of the first times I encountered this notion of sort of a protocol stack. What a protocol stack is basically you are thinking in terms of sort of incoming pipeline and an outgoing pipeline. And you have both of these lanes, and information travels down one, and then it travels back, maybe after being transformed, it travels back out the other. And these protocol stacks, they compose in really nice ways. Basically, they compose in such a way that it allows you to use a protocol stack to transform a handler with extremely well-defined semantics. And basically how this works is something enters in the incoming lane, and it's processed by all of these things in the stack. So every layer in the stack is processed by everything in the incoming lane, and then it comes out the other side, unless the incoming lane fails. If the incoming lane fails, then as the thing is traveling down the incoming stack, it fails right here. It jumps over to the outgoing lane, that's that same layer, actually the layer behind, and then it travels all the way back out. Okay, so what that basically means is protocol stacks allow you to define modular middleware, where if your middleware handles something on the way in, it is guaranteed to be able to handle that thing on the way out. And also, if your middleware fails, then it is guaranteed that the next layer in the stack will never see it. Okay, you have short-circuiting semantics in a stack. So things come in on one side in the protocol stack, and they travel all the way to the end or until the first failure. If they fail, then they jump over to the outgoing lane, and then they go all the way out for all of the layers that successfully handle the input. So that gives you very, very strong guarantees, which you need if you want to build sane, semantically reasonable middleware. And then every middleware layer has the ability to fail. And if it fails with such a type that allows it to hop lanes and go all the way on the way out, so it can be processed by all the middlewares that processed it on the way in. So, and also if it fails, then it doesn't actually make it out of the incoming lane. And it's only if a value makes it out of the incoming lane, so it has to travel all the way through the incoming lane and come out, that it is fed to the request handler. So this means if you want to create authorization middleware, it's very simple. You authorize it, and if it's not authorized, that layer in the middleware fails, and it will never make it to the handler. It won't even make it to downstream middleware layers. So all these guarantees are really nice. They're really wonderful. They fit really well with more complicated types of middleware. And I think we had a lot of bugs in middleware for a long time. And partially they were caused by not having precise and sane semantics around how middleware should compose. And now finally we have rigorous principled semantics around middleware, how middleware should compose, that sort of learn from what Netty's own concept of inbound and outbound handlers, and J Group's own conception of protocols. They learn from all of these things, and they just add types, and they add, I think, a bit stronger guarantees around failure to enable us to build really robust middleware. I think that's going to allow us to do exactly what we want. And something very interesting about this definition of protocol stack is that it is possible to, if handler is sufficiently optimized, then this definition of protocol stack can be incredibly optimized. It can be optimized because you have all these different layers. All these different layers essentially have this arrow that takes the input and makes an output. And those could be ordinary functions. In many cases, they're not going to have any ZIO effects. And so what you can do is create a pipeline and an interpreter that just basically iterates over an array and feeds things over to the left-hand side and just gets out the right-hand side. If there's a failure, then it just jumps lanes to the outgoing lane, which is another sort of array, and just sort of feeds it backwards in reverse. In theory, it is possible to do that in common cases with zero ZIO effects. So no effects whatsoever, just ordinary functions, straightforward values. It's possible to hyper optimize a protocol stack, and that's going to be a future project. It's not a ton of work. It does need to be done at some point. And I think it's going to make middleware, at least if you compose your middleware at the level of this thing called a handler aspect, then all of those things will be fused together in a single pipeline and applied efficiently to a handler. And you won't have to worry about the current situation, which is every time you're adding a middleware, you are wrapping a handler in a handler. And then you're wrapping that handler in another handler. And so you've got these layers and layers and layers of handlers, which are adding significant overhead to the level of every single request, meaning they'll have a big impact on sort of benchmarks, high performance benchmarks. And with this new definition of the protocol stack, we can get it to where you can take all the common stuff that you want for everything, and you can all fuse it together into a single handler aspect. And then you can apply that uniformly, and you can rely on the high performance guarantees of that part. But you'll still have the slower part. If you really, really want, there's still going to be the slower thing, the route transformer available in the middleware. Oh, and this, by the way, not this one here, but handler aspect implements. It implements middleware. And that's because a protocol stack can transform a handler. So how this implements middleware is by going through all of the routes and transforming the handlers associated with each route. That's how you lift a handler aspect up to be middleware, is you apply that handler transformation to every handler in every route.
So let me
go ahead.
Well, let me come back and hit on a couple of questions here. So there was one question with all this great stuff that's getting added here. How does this fit with Tapir at this point? And I could have said, I don't know if you need to use Tapir now that there's all this stuff along with the endpoints API. But I know there's more to it than that.
Yeah, I think that's a great question. I think first off, if you know and love Tapir, there's no reason to switch from that. If that's meeting your needs, then why not continue to use it? I think, one of the things that we're very passionate about in the ZIO community is creating ecosystems and libraries that really feel idiomatic, ZIO idiomatic, and expose things like environment and scope for resources and typed errors and so on and so forth. And I think you'll find that if the endpoint package, first off, there is a little bit of overlap between what is now ZIO core and Tapir, because there is such a thing as a route pattern, and you can introspect on that. You can see it, you can print it out and whatnot. You could even do a little bit of open API stuff with that. And that's great. That's wonderful. But it does make there a little bit of overlap with Tapir, but still not too much. I think the bigger part of the overlap is with the endpoint package, and the endpoint package is very much like Tapir, trying to be a high-level way for you to define the endpoints in your API. I think compared with Tapir, it's more immature. So probably if you want all the bells and whistles, you might need to go to Tapir to find that. And so if you're using more advanced features, you might want to stick with Tapir, even if you're unhappy with the ZIO integration into Tapir. Another thing to keep in mind is that the endpoint package is 100% ZIO idiomatic, right? 100% ZIO idiomatic, and allows you to seamlessly combine your endpoints, which are your high-level endpoints, with your low-level routes constructed by hand. And obviously, that's going to be, it is perhaps going to be possible in Tapir if you really dig down into the weeds, but you're not going to achieve the performance benefits of doing so. Remember, everything is using this prefix tree in ZIO HTTP. So both your high-level endpoints as well as your more manual ones that have to do more, non-endpoint stuff like serving static files and stuff like that. You're not going to encode that as an endpoint. You're going to encode that as a classic route. But you still want to combine them all together and fuse them together and do high-performance optimization on the resulting dispatch. And you do get that out of ZIO HTTP. In addition, I think that we did some early benchmarks on Tapir versus ZIO HTTP, and they came out very favorable in our direction. And I think, in building endpoint, I have been paying attention to allocations and megamorphic dispatch and all this other stuff. And even though there is room to push it further, it is very lean and mean, and it is designed for performance. So I think that ultimately, when all things are said and done, what the endpoint package is going to give you is a more immature version of what Tapir has that feels a lot more ZIO idiomatic and is really, really fast and just very, very tightly put together. So I think there's room for both. There could be plenty of ZIO users who are using Tapir, and I'm happy about that. And I hope those ZIO users continue to push for integration and support for ZIO HTTP in Tapir, because that benefits a lot of users. And Tapir has been, relatively stable. It's only, I think, with this release candidate that we're aiming for a sort of long-term degree of stability of the API now that we think we've figured stuff out. So if you like Tapir, use it. If you're a little dissatisfied by performance or by the sort of ZIO idiomatic nature of it, or you need to combine endpoints with classic routes, then that's when you're probably thinking about looking at this new stuff.
Yeah. There was another question that felt like a little bit of a setup of, is there a universe where ZIO HTTP can support backends other than Netty? And I said, yeah, the answer is completely. And that's actually something we've been working on at this hackathon that's been going on right now. And we're on the tail end, but if you want to join, you can do PRs over the weekend. We'd love to have you. But there's actually been a ton of work to kind of make sure there's nothing in the public API that is at all implicitly or explicitly depending on Netty. So yeah, it's just the backend we happen to be using right now. And in the future, we'll probably support others as well.
Yeah, that's right. And you did see Netty leaking into the public API a lot. And that's what this hackathon is partially about, is getting rid of that and making sure that there's none of this Netty stuff leaking in, because we don't want to force people to use Netty. And obviously we can't use Netty on Scala Native. So there's got to be support for other backends. And the steps taken at this hackathon prior to the release of the next and final planned release candidate are really essential in moving us to that direction where we can have multiple different backends. It'd be great to have like a lone backend using some of the newer Java stuff and several other different, maybe even a native ZIO backend at some point. I think that'd be really fun.
Yeah. There was another question about WebSocket support. I don't know if you want to briefly show that. I think that's pretty nice in ZIO HTTP.
Yeah, so I think WebSocket, Adam did some wonderful work here.
Biased.
That has greatly cleaned up WebSocket support. And now WebSockets can look as simple as this. You can say, here's my handler. I want to make a WebSocket handler. And here's my incoming channel, and I can receive messages and I can send them. Right, that's the basic operations that you get, and it's just really elegant, it's really beautiful. There was a lot of, not a lot, but there was some complication, I think, in the earlier version that was geared at sort of, high performance and exposed some Netty-isms, and all of that was gone in, it was the last RC, I think, that had Adam's changes in there. It's squeaky clean now. I think if you had a bad experience with WebSockets in another library or this library, and you probably did have a bad experience in this library, then you're probably going to have a way better experience with the new cleaned up. It uses this notion called, or this thing called a channel, which is just a structure exactly like you would expect any other ZIO structure. You can await it shut down. You can receive a single thing from the channel. You can send a thing to the channel. You can send a bunch of things. And then you can map the input and output, and you can receive a bunch of things. So it's really, I think, very straightforward, and it's going to make your web applications simpler than WebSocket applications simpler than ever to create. Also, the client has undergone a lot of changes. The client has, for a while, I think, was just a toy and was not suitable for production, but now it has custom DNS resolution support. It has SSL support. It has the ability to do connection pooling by default, actually. And then it had very poor semantics. At some point, we had very poor semantics here because there was different pathways into making a request actually happen. And as part of the refactoring I did previous to this refactoring, I went here and I cleaned up Z client tremendously. Now it has very well-defined semantics, and it basically ensures that all of this stuff, uniform treatment, and there's only one way to make an actual request, and everything works exactly the way you would think it. So I think we've gone from having a lightweight toy client in ZIO HTTP to having something that is very full-featured, very powerful, and can handle simple use cases as well as more complicated use cases very well. And it's just integrated. It's out of the box. It works. It has reasonable defaults for everything like connection pooling. So if you didn't use the client before, I think if you use something like STTP, STTP was quite better than I think the initial version of the ZIO HTTP client. And now we're at a point where it's way better. I think you should go back and you should try and give us more feedback if there's other ways we can improve on this.
Yeah. Kaninji had a question about the custom auth providing middleware and how it works now. I think that was one of you can tell just by its name, that was one of the more complex things with the middleware and the old representation. So this is someone who's been along the journey in ZIO HTTP.
Yes, so I want to show you that because I think it's a real sort of triumph of middleware. So this is the new custom auth. So, I mean, there's several of these. I can show you all of them, but they can be defined in 6 lines of code. So a big part of when I refactored the middleware, I was trying to give well-defined semantics to middleware, but I was also trying to radically simplify things because we had gotten ourselves into a situation where we supported the right feature set, but the API had a lot of complexity associated with that. So while still supporting the same feature set, I wanted to find a way to take that work to the next level and just radically simplify the implementation. And here you can see there's nothing fancy happening here. In any of these, the fanciest one we have is where we have custom auth that provides context. And so that works as follows. Basically, we create handler aspects. The 2 type parameters have the following meaning. The handler aspect uses some environment. That's because your handler aspects can have ZIO effects, so they can use some environment. But also, they produce context that can be consumed by handlers. So that's a new thing. And this is just a value of some type. And most handler aspects are not going to produce any context. But for example, authentication could produce context. Like if you have authentication middleware, then the context that it produces is probably going to be the identity of the user. And you're going to want to consume that from inside your handler. So that now works with type parameters and not using the ZIO environment. And it works using tupling. So I might have a auth example. I don't know if this one uses custom stuff though. No, this one does not use context. There are some examples of context somewhere in here. Yeah, I don't know exactly where they are, but you can definitely find them in the tests. Oh yeah, let's see, auth spec. Somewhere here, there's going to be. Maybe not here. Somewhere you can find an example of how you create handlers that use context, but you do that basically by inside your route pattern. You go down a different path. Ordinarily, you would specify after the route pattern, you would specify your handler. But you can go down a different path if you need authentication. You can specify your auth middleware here. So the next step in that sequence becomes the middleware. And then after that, once you get to here, your handler aspect, you get back something called a route builder. And a route builder lets you specify a handler that consumes two things, not just the sort of input from the path pattern, actually three things, because you would consume the request as well. So you get the context, you get any input from your path pattern, which might be none, and then you get the request. So your handler actually takes three parameters, up to three parameters in that case, or maybe more if you have a lot of variables in your path pattern, for example, it could take more, but they're all as a flattened tuple basically. So your handler might take multiple parameters, and the input to your handler might come from the middleware context if you're using authentication context, might come from the path pattern if you're using variables, and then there's the request that you have to handle. So all of this is supported, it's all tested, and I think it works reasonably well. You pay a little bit of a tax if you are using middleware that produce context, because you have to specify them in a different place in order to make the type inference work out. But I think it's a reasonable, basically you only pay that tax when you have a route that needs middleware context. And that's not the common case. So you seldom pay that tax, the vast majority of your code, and the complexity is not in the API anywhere, right? There's no complexity compared to the previous version. So I think it's the right trade-off. There's no perfect trade-off here, but I think this is the right trade-off that sort of makes the 90% super easy and very straightforward and makes the 10% possible. And then one more thing I would like to show you. I know my Mac is about to die, but this wonderful this is maybe not super useful for most of you, but if you are generating HTML on the server side, you can now actually do reverse routing. So if you have a route, you can basically get the URL that will map down to that handler. And you do that using the format method. And this is type safe, unlike many sort of ways of doing this in other web frameworks. It's 100% type safe. So you feed whatever variables might be required by that particular route into the route pattern. And then you're going to get out your path, which corresponds to that, which lets you basically print out inside the HTML you're generating on the server side. You can embed links to other routes without having to know what the URLs to those routes are. And all of this is type safe and it's refactor friendly. As you refactor your routes and change where they are and whatnot, you're not going to get any runtime failures. It's all just guaranteed to work. So I'm really happy. That was one of the design goals of this, was to support this use case, and it is very well supported. All right, any final questions before my laptop dies?
There was one question about state of HTTP2 support.
Yeah, that's, I don't think anyone's working on that. It's going to be possible to add that in a backward compatible way. I would say it's going to be possible to add that in a backward compatible way. Netty does support it. It's a matter of sort of tying that into the front end here, but I don't think we'll need to modify the API in any way to support HTTP2.
All right, so if anyone wants to do a hackathon contribution over the weekend, there you go.
Over the weekend, yeah. If you know Netty well.
Well, thank you so much for joining. I think you can see from the number of people we had here how interested people are, obviously to hear from you, but then I think for ZIO HTTP as well. And thanks for the questions, everyone. I think we covered everything, but if there's anything we missed, feel free to follow up on the Discord. And have a great weekend, everyone, and a great hackathon for those who are hacking.
Thanks so much, Anna.
Bye.
See you later.